And what I really want to, my name's Patrick McCory, by the way, and I work at the Arbitrum Foundation. But we're not really going to talk about Arbitrum per se during this workshop. What I really want to do is give people here an appreciation for what does it mean to scale something like Ethereum? What are the scalability bottlenecks for Ethereum? And hopefully by the end of this workshop, you'll have an appreciation for why we should even care about rollups as a way to scale Ethereum. So it's a bit like a history talk, going back to basics, and hopefully picking up along the way how we sort of struggled to scale this network. So back to basics. How does something like the Ethereum network work? So as everyone's aware, we have a blockchain, block 1, block 2, block 3. And inside a block, we have a list of ordered transactions. And the fact that transactions are ordered is critical when you think about stuff like MEV, front running, back running, sandwiching. It's all enabled because we have a canonical history of all transactions, and all transactions have a single ordering. Now, what about Alice? Alice is an inspector, and Alice wants to understand, or at least Alice wants to see what is her balance on Ethereum. And she wants to be convinced what her balance really is. So what she'll do is she'll join the network, download the blockchain, and execute the blocks in order. Block 1, block 2, block 3, up to the most recent block on the network. By processing the blocks, what Alice should end up with is a copy of Ethereum's database. And then she can check her balance, and she can say, yep, I have 1 or 2 coins on the network. So if there's one takeaway from this workshop, if there's only one takeaway that you guys remember, the whole point of a blockchain is just to allow anyone to compute a copy of the database. It's a bit like a cryptographic audit trail. I execute the blocks in order, and I can get the same database as everyone else. And that's the only thing the blockchain really does. And then the second component is the peer-to-peer network. So Alice wants to send some coins. She's on her MetaMask. She puts in the transaction details. She signs the transaction. And then she'll want to get that out there and eventually confirmed on the network. The way this is achieved is using a peer-to-peer network or a gossip protocol. And the whole point of the peer-to-peer network is to broadcast recent blocks and recent transactions. And I believe today, Ethereum's peer-to-peer network has about 30,000 nodes. Maybe someone in the audience can double check that. But it's a pretty big dumbass peer-to-peer network. It's pretty damn big. If there's 30,000 nodes facilitating this interaction. And of course, you can join the peer-to-peer network. You can download the blockchain. That's where you get a copy of the blockchain. And then, of course, compute a copy of the database yourself. Now, one of the big purposes of the blockchain is so Alice can send her transaction. It'll be sent across the network in a few seconds. And hopefully, a block proposer will pick up the transaction and confirm it and finalize that transaction. So when you think of the miners or the stakers, what these proposers in general are offering is a transaction ordering service. We trust the proposers, the order transactions in our behalf. And generally speaking on Ethereum, they'll pick up the pending transactions ordered by fee and then confirm them based on, whatever's going to pay them the most money. So they're trusted to do this. We trust proposers to confirm transactions. But thankfully, we don't really have to trust them because they have a financial incentive to do that. The more transactions they confirm, the more tips they pick up, the more money that they make. So again, the user sends a transaction to the peer-to-peer network, and then it'll eventually reach the block proposer. Now, what's important here is that the transactions are kept. So if you're running the node software, so you're running Go Ethereum or Aragon or Nethermind, every node client has a special piece of storage called the mempool, which is really just the pending transactions. They're not ordered, and they're just waiting to get confirmed in a block. It's really to prevent flood attacks on the network. So they're all, every block proposer has the same mempool roughly, and of course they'll produce a block. They'll produce a block that confirms these transactions. They'll send it to every single peer in the network. That takes about 1 or 2 seconds. And every single peer in the network will get the block, execute it, check that it's correct, and then they'll update their copy of the database. And so when you think about this process, all that's really happening is that the block proposers propose a block, send it to the network, and it's a bit like a batch update. Every 12 seconds, there's a new block and there's a new batch update for your database. And that's basically, in a nutshell, how something like Ethereum works today. And what's really nice about this system is that because it does work, by the way, because hopefully we've all used it, I don't know. Raise your hand if you've used Ethereum before, let's check. Awesome, look at that. So everyone realizes this does work to an extent. What you get from this is a global bulletin board, a bit like this screen. Everyone in this room can have a copy of exactly the same database, so they have a consistent view of what, the state of the network, the smart contracts, the exchange rates, whatever. And what can you build with this? Well, you can build auctions, voting, tokens, transfers, gambling, NFTs and art speculation, trading, MMs. And that's all enabled because everyone in this room can have a consistent view of the same database. This single database is widely replicated. So where does scalability come in? If this is how the system works, what does it mean to scale this type of system? Well, we have to consider two actors. The first are the block proposers. Really, when we think about scalability, what are the minimum resource requirements needed to be a proposer on the network? In Ethereum, that is, what are the minimum hardware requirements or bandwidth requirements to join the proof of stake protocol? What's your minimum compute, bandwidth, and storage? And as part of this, as we're going to see, one of the parts of it is, can the block proposers propose the blocks on time so everyone gets a copy of it before the next block? But the flip side to it was really makes cryptocurrency special. What are the minimum requirements to validate new blocks in real time? So everyone in this room, what are the minimum requirements for you to run a node, process blocks in real time, and compute the exact same database as everyone else? So what we really care about when we think about scalability is compute, bandwidth, and storage. Keeping in mind, how do we decentralize both of these actors so we can maximize who can participate in the network? So scalability cares about resources and that right balance between proposers and verifiers. It has absolutely nothing to do with transactions per second. So if you leave this workshop and you say, oh, Paddy was telling me that TPS is the source of scalability, you never took this workshop, guys. Nothing to do with TPS. TPS is like a proxy of this problem. So back to basics. We spoke about the block proposers. They offer an ordering service to the network. We spoke about verifiers. Anyone in this room can download the blockchain, process blocks, and check that everything's correct. There's a peer-to-peer network, and we spoke about scalability. So what are the scalability problems faced today? And my goal here is to give you a taste of those problems. So first, we're going to start with bandwidth as the resource. How long does it take for a transaction to get across the network? And in this case, we're going to assume the entire system's honest. All the block proposers are honest. Everyone in this room's honest. The peer-to-peer network's honest. There's no malicious behavior. It's the ideal, is the best case setup. So when we think about bandwidth, what we are really talking about is the fork rate. And raise your hand if you've heard of the fork rate before. Awesome. A few people. Great. That's a perfect audience then. So what do I mean by the fork rate? So let's say there's two blocks created at the same time. Block proposer A created block 3A, and block proposer B created block 3B. The issue here is that we have two competing blocks, and they're both valid blocks, but only one block can get in the blockchain. So let's just say I created a transaction, and I sent Alice 1 ETH, and that gets confirmed in block 3B. Okay, so Alice is going to get 1 ETH as long as block 3B remains in the blockchain. The issue that arises is what if 3B gets discarded? Block 3A gets minted, then block 4, then block 5. So the top part becomes a canonical chain. Block 3B, it's not part of the chain, it gets discarded. So in this case, out of 6 blocks, we have a 16% fork rate. And what that really means is that the network's not reliable in the short term. I can get a transaction confirmed, unconfirmed, reconfirmed, and then maybe discarded. And that sucks from a user experience. If your transaction gets a confirmation, then that should hopefully lead to more confirmations, and you shouldn't be in this state of limbo where it's sort of going to get confirmed, then it doesn't get confirmed, then it gets dropped, then it gets back in. That doesn't help the user. So that's what the fork rate's about. How do we minimize competing blocks so there's only one canonical chain that's always being built? And again, as I mentioned, why do we consider this? Because if the blockchain's tip's unstable, it's just bad for the user because the network's not reliably confirming transactions. And as part of this, when you think about the fork rate, there's two components to it. One, how long does it take for a block, what is the length of time it takes for a block to reach the entire network? So if I produce a block, how long does it take for everyone in this room to get a copy of that block? And the second component is frequency. How often are blocks created and produced? So let's use some simple examples. Big versus small blocks, if you remember the block size wars. So let's consider a small block world. There's a 1 megabyte block every 10 minutes. So in this scenario, it's 1 megabyte, it's really small. It's going to zap across the network really fast. Within, maybe 5-6 seconds, everyone in this room can get a copy of that block. You will have processed it and you would have updated your database. And if there's a block every 10 minutes, then there's a very low probability that a competing block was created by the time your block was getting across the network. So there should be very few forks, intuitively. The flip side to that is, what if there's a 1 gigabyte block every 30 seconds? If there's a 1 gigabyte block, then it's probably going to take me a minute to get it to everyone in this room. So everyone gets a copy of my block. So as the block's going across the network, maybe someone over there in the front row, you're a block proposer, you create a competing block. You didn't get my block in time, you're still working on the old block, so then you create your block, then you broadcast that out. And then you have 2 gigabyte, you have 2 blocks going out and trying to get across the network. And then maybe, of course, there's a third block, and obviously this isn't working. This sucks for everyone involved because, one, the network is unstable, and 2, you're just wasting bandwidth. There's only one of these blocks get confirmed at the end. So the question is, can you get really good numbers on this? And for the sake of time, actually, not for the sake of time, I got it here. So to put some good numbers on this, and this is about a year old now, I think the slide is. In Ethereum, blocks are about 120 kilobytes, and they're every 12 seconds. And on Bitcoin, they're 1.2 megabytes, and they're every 10 minutes. So in proof-of-work Ethereum, before the merge, there was a fork rate of about 5 to 6%. And that clearly sucks for the users involved. With proof-of-stake Ethereum, it's less than 1% now. And that's really because proof-of-stake Ethereum are synchronous. There's strict deadlines to do stuff. So people know when to create a block, when to validate a block. It's a much more structured system. Where on Bitcoin, there's a fork every 1 to 2 months. They're so uncommon that BitMEX writes a blog post when there's a fork. Because it's a big event in Bitcoin that there was one fork and one stale block. So what's the ideal block size and interval? That's always a moving target based on the composition of the peer-to-peer network. So there's a research paper called On Scaling Decentralized Blockchains. It's from 2016. I think at the time it recommended a 4 megabyte block every 1 minute. But back then I was like, God, that's like 8 years ago now. The network's way more effective than it was back then. But when you're thinking of this question, this trade-off, the ideal block size and interval, the question's really, what percentage of the world's population could download that block, process that block, and pass it on while keeping up with the network? If I can only process a block every 10 seconds, well, there's a block every second, then I just fall behind. I get the block, I process it, I pass it out. Oh no, now there's 10 blocks. And then I just can't keep up with the network. I can't keep up with the latest state. So it's just not useful for me. I'm always behind. So you have to really consider, if someone's in Africa, Australia, US, Hong Kong, whatever, you have to consider, 90% of the population based on the peer-to-peer network today, what are the realistic settings that you could put so they can actually get the blocks in real time? So that's bandwidth, fork rate. Hopefully that gives you a sense of the bandwidth problem. The next one is hardware and compute. And really the question is, how long does it take to compute a fresh copy of the database from scratch? So if you download Go Ethereum today or Bitcoin Core, how long does it take you from scratch to get up to date with the network? And James Mlop does an experiment every year testing exactly this problem. And it's a great, I'm sure he'll do one in a few months. It's normally around the new year. So look out for this blog post. It has a relatively beefy machine, 1 terabyte storage, 6, I guess, Core i7, some CPU. Regardless, let's look at the results. So in 2021, he was able to sync a Bitcoin full node from 2009 till today, every single block in about 400 minutes. That's pretty damn fast to process 14 years worth of transactions. On Ethereum, his Go Ethereum node ran out of disk space, so he wasn't actually able to complete the task. And this was after 5 days and 21 hours, and then he, based on the work, he suspects it would take 10 days to sync Go Ethereum. Again, this is 2021, 2 years ago. But the most interesting part of this is at the time of the crash, Go Ethereum had 15 terabytes reading from disk and 12 terabytes writing to disk. And as you're going to see, the database isn't that big. The database is like 600 gigabytes. So why is there so many I/O operations? Seems a bit much. And actually what he worked out was executing transactions is not the bottleneck, is I/O, reading and writing to the database itself. That's the bottleneck at Ethereum today. So then if you look at Aragon, because he ran Aragon, because he really does just want to synchronize a node, with Aragon he was able to finish it, and interestingly Aragon's I/O was much better. It went down to 1.9 terabytes and 1.8 terabytes. So the question is, why would it take 10 days to sync Go Ethereum, but only 2 days and 16 hours to sync Aragon with a lot less I/O? The reason is because of this tweet. And let me give you some detail. So in a block header, we have something called the state root. The point of the state root is that it's a single hash that represents a commitment to the entire database at this point. So you can consider the database, you build a Merkle tree or Patricia tree, you end up with a single hash, and you put it in the block header. The reason why you have this is because if I want to prove what your balance was at a certain block, I can use the state root to prove an entry in the database, so I can prove to you what your balance is, or what the size of an LP pool. I can prove to you information about a block at a certain time. So that's why it exists. But Aragon stopped checking that. It just skipped that check altogether, and it was like, whoops, not going to check the state root, it's too expensive. So what they would do is you would synchronize from the Genesis block up to the latest block. Then if I remember correctly, they would randomly sample previous state roots. And with the random sampling, they would get some guarantee to say, well, there's probably all the state roots are correct if you only check a subset of them. But that's interesting. To get over the I/O issue, you have to stop fully validating blocks. So the surprising takeaway here is really executing smart contracts in memory. It is expensive, but I/O is actually the real bottleneck. And other blockchains, this is again just from his tweets. In Definity, they just give up on the issue. You had to buy your hardware from an approved supplier to run a node. And even in Solana, again, this is 2021, they have these crazy requirements that most people aren't going to have at home, like 128 gigabyte RAM. I don't know what it is today. That's from 2021. But it's just, and this also isn't a wrong choice. It's just a design choice on how many people in this room could validate the blockchain in real time. That's really the decision here. And obviously there's a spectrum. So that's compute. Hopefully that gives you a taste and a flavor on the computational problem. But what about storage? So when we think of storage, there's 3 different things that we store. One is the database, the mempool, those pending transactions, and then the blockchain itself. And the question is, what's the minimum data required to run a node and validate new blocks in real time? So a copy of the database, and I think this is from 2022, the Bitcoin database is really small. It's about 5 gigabytes. It's not that large. Where when I checked Ethereum, a normal node, a full node, which we can talk about later, it was about 700 gigabytes. It's probably a bit bigger now. And then an archival node was you'd only run if you're an explorer, because it's really making it easy to look up historical data. It's 10 terabytes for Ethereum back then, or about 2 terabytes for Aragon. But the problem with the database is that the database never gets smaller. And I'll illustrate this with a question. How many people, who in the audience writes smart contracts? Raise your hand if you write smart contracts. Okay, raise your hand if you delete data in your smart contract. No one. No hands. Look at this. Great citizens of the world. And that's important because the database never gets smaller because no one deletes data. So this database is always growing. If I remember right, this is like 2 years ago, I think on Polygon, and this was an archival node, so, pinch itself there, but I think their database was growing, or their storage requirements were growing, 1 megabyte every 2 seconds. That doesn't sound like a lot, but eventually it gets to 15 terabytes, and it doesn't fit on AWS anymore, and it never gets smaller. So that's one of the big bottlenecks on Ethereum. A copy of the blockchain for Bitcoin is actually quite big. It was about 400 gigabytes at the time, and that's just because Bitcoin transactions are bigger because of the UTXO model than Ethereum. And on Ethereum, it's about less than 200 gigabytes when I had this screenshot. I think that was a year ago. It's probably not that much bigger now. Maybe someone in the audience wants to check if you have Ethereum installed. And then finally, the mempool. The mempool's, that's like back of the envelope. It's about 100 megabytes. It's not really a bottleneck when it comes to scalability. And it's really just to stop flooding of the network. If I hear a transaction once, I don't really want to send it again. So that's, to give you a flavor of the resource requirements. We looked at bandwidth, compute, storage, and we're really just understanding, okay, these are the problems on Ethereum today when it comes to scalability. So pop quiz. I actually forgot I had this here. Why do we have the gas price and a gas limit on Ethereum? The reason why we have it is because we need to prioritize access to block space. Block space is our most scarce resource. So if there's high demand and high congestion, the gas price goes up, and only the people willing to pay the most money can get access to the block space. But the reason for the gas limit is really to limit the maximum growth of the database and basically compute on the network. If the gas limit is 30 million gas over a period of a year, we can have a rough estimation to say maybe the database will grow 20 gigabytes this year. Where if the gas limit was bigger, then of course the database would also get bigger because it's just cheaper to transact. So the gas limit's really there to prevent the growth of the database, and then compute is like the second priority after that. So again, a bit of a summary. We looked at storage, compute, bandwidth. And the problem is if you just blow up the transaction throughput, you want to support 1,000 transactions per second, the blockchain just becomes unstable. It leads to more forks, it's bad for the users, and then people in this room, you won't be able to keep up because there's too many transactions, database gets too big. Like Jameson, couldn't run Ethereum, doesn't help. So to the final part is fighting back. How can we scale something like Ethereum while trying to adhere to the principles of being decentralized, i.e. maximizing who can participate as a proposer or as a verifier running a node at home, so you can just have a copy of the database yourself. So scalability has 2 goals. 1, reduce the fork rate. Fork rate should be highly reliable for everyone involved. And 2, maximizing the population of nodes. So everyone in this room can run a node and verify that the database is correct and have access to the database for whatever dApp you're building. And there's lots of widgetry tricks we can do to bring this down. Lots of widgetry tricks from engineering. You can compress data over the wire. Maybe you have a private relay network. Bitcoin had that for a very long time, where you bypass a peer-to-peer network completely and the blocks are sent directly to the miners. Maybe a parallel execution. If transaction 1 and transaction 2, they don't interfere with each other, why not run them at the same time? So they're parallel and you're not just running everything sequentially. Or maybe you make better use of the bandwidth using special cryptography tricks. So this is needed, and this should be implemented. So basically, given your set of resources, you're making the most efficient use of those resources by doing this. So you don't increase, the storage or the bandwidth or the compute, but you're making better use of the resources that you have. But it only goes so far. There's only so many widgetry tricks you can do at that level. as we saw with the block size wars and over the past couple of years. So is there another way? Is there another way to solve this problem? And the way we like to think about it in the L2 world is, can we protect the peer-to-peer network? Can we protect decentralization of the peer-to-peer network such that the peer-to-peer network can check the results, but you move all of the hard work out of the network? So Ethereum is no longer storing the database. Ethereum is no longer computing all the transactions. Ethereum is just checking the result of what happens somewhere else. So all the hard work happens over here. You can have different resource requirements over there. But on Ethereum, we just check the results. We don't actually do the hard work ourselves. Can we do that? And this is sort of the play on, the monolithic architecture versus the microservices or the modular, sort of narrative or theme. Right now, Ethereum is trying to do all the work itself. Can you move the work elsewhere? And what this has sort of led to is renaming the resources the special layers. So compute is now the execution layer. Bandwidth is now the data availability layer. Can I guarantee the broadcast of data and it reaches everyone in this room at a certain time? That's now the DA layer, but it's really just bandwidth. And then 3, storage, the settlement layer. Where is the database that records all the assets, and it is the source of truth itself? And it may look like a simple renaming, but by renaming these resources to layers, we can solve each problem individually and, of course, hopefully scale the network. And so for the final part, because we only have a few minutes left, off-chain in the multi-chain world. So the way this works for the roadmap, the roll-up-centric roadmap is you take your coins, you lock it into a bridge, then you unlock it on an off-chain system, you transact there, then you bring the coins back to Ethereum. So what is the off-chain system? So let me ask the audience, who's ever used an exchange before? Who's used Binance, Coinbase, Bitstamp? There you go, we found the people who bought the shit coins. I'm only joking. But what's important is that this is how we've actually scaled the network for the past 14 years. You take your coins on Ethereum, you put it in this bridge, then it pops up on Coinbase, Kraken, Binance. You perform all your transactions there, then you bring your funds back. So this is actually how we've already scaled. Bitcoin and Ethereum in the early days were an interruptibility solution for the exchanges. You buy your coins in Coinbase, you move it to Binance, you mess them up with the shit coins, then you move your funds back. And people aren't actually using the cryptocurrency, they're using the exchanges. But the problem with exchanges is one, most people here are aware now, they're fully custodial, they can freeze our funds, they can confiscate our funds. Maybe they'll use our funds to buy some villas in the Bahamas. They can lose our funds. They're not auditable. I can't check if they're solvent. I can't even check if they've been audited. There's no way they audit the system to make sure that every transaction process there was actually correct. We just have to trust the operator to do that. And that sucks. So could you have the off-chain system to be a blockchain? Where I take my coins, I bridge it over, it's another blockchain, I transact there, and because it's a blockchain-based system, I can verify the blocks, I can download the blocks, I can execute them, and I can check that everything's correct. And then eventually I bring my funds back to Ethereum. And what's nice here is that if you can do this, Ethereum becomes a settlement layer, and all the hard work happens on this other blockchain system. And with the bridge, you can then check your assets against the liabilities. The assets are on Ethereum, liabilities on this off-chain system. You can check that they're correct. You can have full-time audits, or real-time audits. It's just a much better tech stack for building these type of off-chain systems. And that's what we're trying to build roll-ups. When you think about roll-ups, they're really just replacing these custodial services. The Arbitrum, Starkwares, Optimism, ZK, Sync, Scrolls. It should eventually feel like you're interacting on an off-chain system, but in a way where you don't have to trust the operator. And that's my final slide, so thank you guys for listening.